In this video, we're going to pick up where we left off with the physics problems. Problems 1 through 4 included questions on 1D kinematics or one-dimensional kinematics. These next two problems with all of their parts are talking about vector mathematics. So in this example, you walk 10 meters in a direction 20 degrees west of north. You turn and walk 25 meters in a direction 60 degrees west of south. Our objective is to find how far we are from our starting point and what's the compass direction that you're heading, and we'll report that two different ways. So we saw this in our lab last week. We've got to draw two vectors and connect them tail to tip in order to find this appropriate answer. Now, what I like to do is I like to draw these mini XY axes to help me understand the position and the direction that we're heading. So I'm going to draw one right here because I know that I'm at first traveling 20 degrees west of north. So that helps me understand that if we were traveling north, it would be in this direction, but 20 degrees west of north is over here. And I'm just going to mark the angle, and it may be small on your screen. Let's see if I can make that bigger. So this is 20 degrees west of north, and we're traveling a distance of 10.0 meters. Then at this new position, so at the end of that vector tail, so at the end of this vector, I'm going to draw another XY plane, or I suppose axis is a better phrase. This time we're traveling 60 degrees west of south. So if I'm thinking of the vector direction this time, south is in this direction, and if I travel 60 degrees west of that, that might be all the way over here. Now, this vector has to be longer than the first one. In fact, it's more than twice the length because it's 25.0 meters. And this angle measure from vertical to this angle is 60 degrees. Now, hopefully you recognize that there is a resultant vector from the beginning to the end, and it's this resultant vector, we call that R. So we'd like to calculate the length of this, and we often indicate that length with these double bars. Some textbooks use a single bar. I prefer the double. And so that's going to give us our magnitude, the length of this arrow. Magnitude has pays no attention to the direction here, so the length of the vector is represented by R. But we would also like to know the angle measure associated with that too, and we of course measure our angles from the positive x-axis where we started the travel. So the first thing we've got to do is find the length of this edge of the triangle, and we can do so using the law of cosine since we have a side angle side triangle. An SAS triangle leads us to the law of cosines. And in this particular case, the angle measure up here included in between the two side lengths is not 60 degrees, but it's actually 60 degrees plus 20 degrees, because recall, we've got, say, a vertical line here and a parallel vertical line here cut by a transversal. So alternate interior angles are equivalent. So this component of the angle is 20 degrees. And this one's 60 degrees, so we've actually got a triangle that contains an included angle of 80 degrees total. So from trig class, you would have learned about this law of cosines formula. What I'm going to do is modify it just a little bit. C, the lowercase c, does represent the side length that we're after, but since the formula includes a c squared, and I want c by itself, I'm just square rooting both sides, and I've got this formula as a result, where lowercase a and b represent our two side lengths, in this case 25 and 10, and theta, or we'll probably use a capital C here more often, this angle measure C is the included angle in between. And I've made the substitutions now so that you can see the result, and I've also changed letter C to the magnitude of vector R, just so that we're using appropriate terminology here. This is something I can bring to the calculator and compute a result. And before I do, I want to double check the units here. I've got meters squared plus meters squared minus meters times meters. Well, that's meters squared times some sort of ratio. So there's no unit associated with cosine. Underneath the radical, we've got all these meters squared added together. So when we take the square root of that, our final unit will be meters, which is good because that's exactly what we're looking for in terms of the length of this vector. Now I'm only going to keep 3 significant figures here because our data points were supplied with three significant figures. And as it turns out, the computed result is 25.3 meters in length. So clearly that gives me the answer to part A. We know the distance that we are from our starting point. That's the magnitude of travel. But we need to know the compass direction and report this in a couple different ways. So in order to find the compass direction, this is where it gets to be a little bit tricky. We need to find another angle measure inside the triangle. And so I'm going to use the Greek letter alpha to represent the angle measure of this triangle. And this sketch, now we got to be careful here, this sketch is not necessarily drawn to scale. I did not measure these lengths and I did not measure these angles. So hopefully the sketch is accurate, but it is possible that it isn't. So if I'm looking for alpha, I'm going to switch to the law of sines to help me solve that. The law of sines said that sine of A divided by length A is equivalent to sine of B divided by length B, where capital A and lowercase a, capital B and lowercase b are side lengths and angle measures that are directly across from one another. So with the law of sines known, let's go ahead and set that up. I might say something like this, that sine of 80 degrees over 25.3, since these two values are across from one another, must be equal to sine of alpha, this angle measure, which is across from 25. Now when we cross multiply and divide, the result's actually going to leave us with sine theta. So we know that 25.0 times sine of 80 degrees divided by 25.3 equals alpha. I said theta before, sine alpha. And in order to get alpha by itself, we need to apply sine inverse to both sides. So sine inverse applied on both sides will leave alpha by itself. And using my calculator, I get a result of 76.68. So we'll call that 76.7 degrees. Now alpha is 76 point some odd degrees. That's kind of interesting because I think our diagram is going to be off a little bit. If the 76 degree angle measure references off of this position here, I don't know if you can see that because my diagram is getting kind of full, we're actually rotating 76 degrees beyond 20 degrees, and that actually puts us below the x-axis. So this diagram isn't quite correct. I don't know if I didn't get my length of the vector drawn appropriately, or maybe the angle was off just a little bit. So it kind of looks to me like we ended up in this position down below. The reason why I say that is because 20 degrees plus 76 degrees is greater than 90. So that tells me that we're pushing down below. And so unfortunately what that means for us is that the resultant angle, this isn't a rule that you can just memorize here, but we've got to think about it a little bit more carefully. The resultant angle is actually going to be 90 degrees plus 20 plus 76.7 degrees. And the reason why I have to add all three of those is because when we report this angle, one way that we can report that is relative to the positive x-axis. And so if I think of my axis that's drawn here, 90 degrees is the measurement of rotation from the initial position to this mark. Then we had another 20 degrees beyond that for the first vector arrow, and then another 76 degrees to land on this blue vector arrow, this last vector here. So it's all three of those angles together that represent the theta value relative to the positive x-axis. And that result ends up being 186.7 degrees. And hopefully that makes a little bit of sense. After we add those two vectors together, we realize that we're now traveling 25.3 meters in this direction, or I'm sorry, 25.3 6.3 meters along this vector arrow, and the angle that we're traveling is 186 degrees, just beyond horizontal here. Now, a second way that we can report this angle measure is not the angle measure relative to the x-axis, but maybe relative to some westerly direction. And so since this is 6.7 degrees difference below the x-axis in this negative direction, an alternate would be to say the angle measure of our resultant vector is, say, 6.7 degrees south of west. And there are a variety of others that you can answer, but that's just one alternate. So there we go with our two solutions for the angle measure as it's reported, as well as the distance or the length that we've traveled from our starting position. Now, I certainly believe that this oblique triangle method is the way to go when we've only got a combination of two vectors. It may be a bit confusing, but as you get more comfortable with it, it tends to be a little bit faster than the component method. However, the component method is pretty good when we have multiple vectors, and in this case we've got 4 vectors that are working together. We've got a 3D printer that needs to print a test skirt in order to verify position calculations with a new piece of software that's been installed. So a skirt is, if I've got a 3D printed object that takes up this space on the bed, a skirt is a test print that goes around the outside edge of that object. And so we're trying to figure out the dimensions of that outside edge. And we're going to see if the print head returns to its original position precisely. So what I would like for you to do is to pause the video right now and try to draw these 4 vectors. They don't have to be perfect, but try to draw them in a representative fashion. The first arrow, first vector is 16 degrees counterclockwise to the upward direction. So what I mean by that is this: if we were facing upward and traveled counterclockwise, that would be in this direction, 16 degrees. Then we draw another angle clockwise to the leftward direction. So if we start leftward and travel clockwise, that's up in this direction. Try to make a rough sketch of what this would look like if we made those moves in these directions along with these lengths. And when you're done, you should see a diagram that should close itself. The final vector should land in the same position that it started. Now, drawing involves some error. Measuring angles and drawing lengths involves some error, and we're going to either confirm or refute the error by using the math to support that. So again, pause the video now and try drawing that and see what you can come up with. I'll show you my result in just a minute. So here's what I came up with, and I'm not saying that it's perfect, but I think it does represent the situation pretty well. At the beginning of each vector, I imagined a mini XY plane here, and so I drew this first angle 16 degrees counterclockwise to upward, and then I drew another, or imagined another intersection here, and I drew this angle 29 degrees clockwise to leftward, etc. So at each of these intersections, I imagined a XY axes put in place, and that allowed me to understand the direction of travel for each of these vectors. Now again, with this rough sketch, if I traveled 2.5 centimeters and then 3.2 in this direction and 5 and 4, it kind of looks like this thing's going to return back to normal. So let's do the math and see if that's truly what happens. And we'll do the math this time using what we call the component method. I'm going to make some room. I'm going to move this from our last example off the screen just a little bit. So with the component method, we're going to use regular right triangle trigonometry to find the horizontal and vertical component of each vector. So I'm going to use my orange marker here for this first vector, and you could imagine, hopefully, that a right triangle is formed with the vector acting as the hypotenuse. If I wanted the horizontal component of this triangle, I could think of it as the opposite side of this triangle, and then the vertical component is the adjacent side of this triangle. But what would make life a lot easier is if we continue to reference our angle back to the positive x-axis. In doing so, we can produce some shortcuts with our calculator and trust that it will produce the correct result for us. So rather than thinking about this triangle and then changing its orientation for each one to follow, as you can see here with the different colored triangles, what we'll do is we'll accept this general rule. If I want the horizontal component of any vector, as long as we choose the angle measure relative to the positive x-axis, the horizontal component, I'll call that x, and maybe I won't use the vector notation here. That would be the magnitude of the vector in question, so the length of the vector in question, times cosine of the angle measure in question. And the vertical component is going to be our magnitude, or the length of the arrow, length of the vector, times sine of theta. Now this should look familiar to you because this falls right in line with our definition of the x and y coordinates on a unit circle, and we're just using the multiplier in front to enlarge the unit circle. In vector number 1, we would say something like this. The horizontal component of number 1 is equal to 2.5 times cosine of not 16 degrees, but we'll call this 116 degrees. Sorry, I got to do my math correctly. 106 degrees. That's 16 degrees beyond 90. For number 2, vector number 2, we'll call that one 3.2 times cosine of not 29 degrees, but 151 degrees, because again, this 29 degree angle measure, it measures off of the leftward direction. We want it measured off of the positive x-axis. So that's 151 degrees. X3 we will measure at 265 degrees, so that's 5 times cosine of 265. And for X4, well, that one's oriented correctly for us, so we'll call this one 4 times cosine of 14 degrees. And this is very nice because if I sum all of these horizontal components, then the end result is going to be the difference between our starting position and our ending position. And we would like for this to be 0, because if it is 0, then that confirms that the horizontal position of our print head is 0 units horizontally different from the beginning. Well, what do we get when we add these up? Well, unfortunately, this adds to negative 0.0425, and I'm showing 4 decimals here just so that you can see the result. I'm not paying close attention to significant figures. So since this end result is not 0, it is leftward of our target by 0.04 centimeters. So we're about 4 millimeters off. And on a precision component, that might be a pretty big deal. So we would probably want to fix that. But the end result is 0.4 centimeters to the left, and I know that it's leftward because of the negative sign indicator. Now we can do the same math with the y components. Y1 is going to be 2.5 times sine of 106. Y2 is 3.2 times sine of 151, and so on. And again, the sum of these component vectors we would like to see to be 0, and perhaps an explanation is in order. Let's think about all these vertical components for just a second. If I imagine this vertical component, that's an upward facing arrow. This one's also an upward facing arrow. So if I stack those two on top of one another, we'd be facing in this direction. But then I've got a downward facing arrow for my next vector, which is this one, and then I've got an upward facing vector for this one. So if I add together all of those upward facing vectors and subtract this downward facing vector, the idea or the hope is that we'll level off, we'll come back to 0, and any difference between the two is going to be reported with this computation. We can talk more about the math behind that when we see each other in class, but that's essentially what's happening here with each of these components. Now, this result comes out to be negative 0.0587, and so that tells me that we are actually below our target just a little bit as well. So the new software that was installed evidently has not completely agreed with the motion of the print head, so we've got a bit of a problem. So since it does not return to start, let's determine the correct magnitude and direction of the final vector so that it would have returned it to center. So this final vector is one that we'd like to change. Let's correct this one. We'll leave the first three alone, and then we'll make this final vector the correction vector. So what we could do here is essentially the same math as before, only eliminate this fourth vector. What this will do for us is it'll tell us the position of the print head after the first three steps are done. It'll tell us where we are here. And if we know where we are here and where we would like to be, then we can actually calculate the correct magnitude and direction that would bring us precisely back to start. So I've rewritten those computations, and since I've got these expressions stored in my calculator already, I'll just repeat the calculations without that final vector. And I end up with negative 3.9237 for the x component, and I end up with negative 1.0264 for the y component, the vertical component. And so what this is telling me is that this print head position here at the end of the first three moves is 3.9 units to the left of start, and it is 1.02 units below start. So that's the resultant, if you will, of our movement. What I would like is the equilibrant, the same magnitude, just the opposite direction. Well, if I'm leftward 3.9, I should actually move rightward 3.9, and if I'm downward 1.2 units or 1.2 units below the target, then I need to move up 1.02 units in order to return to target. So the direction is just the obvious, or just the opposite. Hopefully it's obvious, but it is the opposite direction of what we just calculated. And from a trigonometric perspective, if I need to travel 3.9 units to the right and 1.02 units above, then certainly I can compute the angle measure, which would be here, of travel, and I can also compute the, actually that's the wrong symbol. I'll use E for equilibrant. I can calculate the magnitude or the length of that equilibrant pretty easily as well. So it doesn't matter to me which one we solve first. I wrote theta first, so I'll go ahead and use that. Now theta can be calculated with the opposite side and the adjacent side of this right triangle. That's done using the tangent formula. So if I don't have the angle measure but I want the angle measure, I'll use tangent inverse. And we'll take the opposite side length, which is our vertical component, 1.0264, divided by our horizontal component, 3.9237, and the computed result here should give us our theta value, the correct angle that would return the print head back to start. And that appears to be 14.6595 degrees. Close to the 14-degree angle, which is good, but not exactly the same as precisely 14 degrees. Now this equilibrant vector, that's just the length of the hypotenuse, and if e squared is equal to a squared plus b squared, then this result is equal to the square root of 3.9237 squared plus 1.0264 squared. And that ends up being 4.0557 centimeters, so not quite the 4 centimeters of travel, but 4.055. Now, in reality, I don't think a 3D printer would correct itself this way by just fixing one vector at the end, but I chose this problem so that it would illustrate this component math. And to be perfectly honest, both of these questions could be completed using either method, either oblique triangles or components of right triangles. If you're looking for one single method that works pretty much all the time, then I would probably commit to learning the component method and understanding how to apply it to a variety of situations. Because honestly, that one just handles multiple vectors just a little bit better. With oblique triangles, we'd have to create several oblique triangles in order to recreate this diagram, and several oblique triangles are going to be harder to work with than several right triangles. So I think this is a good stopping point for this video. We will pick up the next video with our 2D kinematics examples, and then we'll finish out the lecture